So, in the last lecture we have discussed the limit of the function f x when x tends to c, and in that case we have seen many examples where the limit of the function f x does not exist, and the reason for this, either the function is not defined at the point c, means it goes to infinity or minus infinity, or maybe it has a different limit along a different path, means when you take the right hand side the limit comes out to be different than the left hand side limit. Okay. So, then we say the function does not have a limit. For example, if we take the function f x as the signum of x, we have seen the limit of this function f x signum of x when x tends to 0 does not exist, because the reason is very simple. When you take the left hand side, the limit comes out approach to minus 1, right hand side the limit approach to plus 1, and at the point 0 it is 0. But however, if we consider only the set A over which the limit is taken, which is either in the right hand side of this 0 or maybe the left hand side of the 0. Say if I take the c greater than 0, means c infinity interval if I take, and then find the limit of the function f x over the interval c infinity where the c is positive, then the limit of this function right hand limit exists, because there is no scope for going below of this. Okay. Similarly, when you take minus infinity say c to minus infinity, then also the left hand limit exists, is it not? So, in such a case, though the limit does not exist, but we can say partially the limit of the function exists when you approach either from the left hand side or from the right hand side. Individually limit exists and may be different, that is a different matter. Now, in such a case, when we define the limit of the function, we call it that thing as the left hand limit. When you approach the point from the right hand side, approach the point from the right hand side, then it is called the right hand limit. When it goes from the left hand side, because the left hand this one goes to here, left hand and right hand limit, and then we say if both the limits coincide, then only we can say the function has a limit in general. Otherwise, we can also introduce the concept of, we will introduce the concept of left hand and right hand limit, which we can say is an extension of the limit concepts. So, that is also called one side limits, that is one side limit, one side limits. Okay. So, let me see first, let A belongs to R and let f is a mapping from A to R. Then 1, if f is in C, if C is in R, if C is in R, is a crystal point of the set A, of the set A intersection C infinity, that is the set of those point x where belongs to A, such that x is strictly greater than C, x is strictly greater than C, then strictly greater than C, then we say that L, a real number belongs to R, L belongs to R, is a right hand limit, of the function f at the point C, and we write which is denoted as, or and is denoted y limit f x tends to C plus, x tends to C plus is L, if if for given epsilon greater than 0 for any epsilon greater than 0 there exists a delta. There exists a delta which depends on epsilon greater than 0 such that for all x belongs to A and x satisfies this condition with and 0 is less than x minus c less than delta, that x belongs to A and as well as this condition, then the mod of f x minus L is less than epsilon. So, for all x with you can write with 0 is less than this. So, this is called the left hand limit. So, here this function is there, this is our interval c infinity, c is this point and then infinity here. So, we can choose here and then A intersection A is some segment. If we take the A intersection C, say A is suppose somewhere here, this is our A, then A intersection C will be this set. So, if we picked up the point x here which are greater than C and if the functional value f x minus L lies between this interval, then we say that the limit of the function f x from right hand side exists and equal to L. That is, we are approaching to C from the right hand side to C. Okay. Then second we define the if C is a point in R, be a cluster point or is a cluster point of the set A intersection minus infinity to C. It means this is the set of those point x belongs to A where x is strictly less than C. Then we say L belongs to R is a left hand limit of f at C denoted by limit f when x tends to C minus is L. If given any epsilon greater than 0, there exists a delta greater than 0 such that for all x belongs to A with condition is 0 less than C minus x less than delta, then we have mod of f x minus L is less than epsilon. So, this is our right hand limit, left hand limit of this. So, we are approaching the C from the left hand side, that is this is the interval C and the approach is from this side. So, when you take the x point here which approach to C from the left hand side, then and if this condition holds, then we say the function has a limit left hand limit at the point C. Okay. So, the left hand limit and right hand limit this way we define, and we have seen the example is that if we look the function sin x, the limit of this left hand limit comes out to be so example is if we take the function f x equal to signum of x and the C is a point 0, then we say the limit of the function f x, that is signum of x, when x tends to 0 minus is minus 1 from the left hand side, while the limit of this signum of x, signum SGN, signum of x as x tends to 0 plus this is first one. So, this is the right hand limit, this is the left hand limit for this. Okay. Now, when we introduce the concept of the left hand or the right hand limit, we look the set A, an intersection with the C infinity if the right hand limit, or intersection with minus infinity to C if the left hand limit. And then if the limit comes out satisfy this condition, then we say limited. However, it is not necessary that always we will have a either left hand limit or right hand limit or maybe both. It may so happen that we may not get the neither left hand limit nor the right hand limit, hence limit will not exist, or maybe sometimes we get the left hand limit, but not the right hand limit, and vice versa, or otherwise or sometimes we can get both the limits, but the value are different. So, this is the case when both the limit exist, but they are not equal, The second example, if I look the function f x which is 1 by x, then what we say is when c is a point 0, then we say the limit of this function x 1 by x when x tends to 0 minus, from the 0 it goes to minus infinity, and limit of this 1 by x when x tends to 0 plus it goes to plus infinity. So, limit does not exist here, of course, and they are different, they divert. Third case is if we look the function f x equal to say e to the power 1 by x. Suppose if I take this function e to the power 1 by x, and then when we take the limit of this function e to the power 1 by x when x tends to 0 plus, or limit of the e to the power 1 by x when x tends to 0 minus, what we will say here that when x tends to 0 plus the limit will be infinity, while in this case the limit comes out to be 0. So, left hand limit exists, but the right hand limit does not exist, comes out to be finite, it is infinity. Okay. The reason of this is simple. Why it is so? Because if we look that any t, for any t greater than 0, we have 0 less than t less than e to the power 1 by t, because the expansion of e, because e to the power z or x is 1 plus z square by factorial 2 and so on. So, obviously, when you write the this is not, this is t, I am sorry, e 0 is less than equal to t less than t, and this is true for all t greater than 0. So, when you write t, replace t by 1 by x. So, what we get is 0 less than 1 by x less than e to the power 1 by x for x greater than 0, clear, for x greater than 0. Now, this if we take a sequence, x n say 1 by n which goes to 0. So, this x n goes to 0. So, what about this 1? From here equation from 1, what we get? The corresponding sequence 1 by x n which is less than e to the power 1 by x n greater than 0 will imply that 0 less than n less than e to the power n, and since this tends to infinity, therefore, this limit will go to infinity as n tends to infinity. That is, when x tends to 0, e to the power 1 by x will go to infinity. Okay. Now, on the other hand, if we replace in this expression, if we replace t by say minus 1 by x, t by minus 1 by x, if x is negative, then minus 1 by x of course is positive ho jaye, then we get from here is 0 less than minus 1 by x less than e to the power minus 1 by x valid for x to be negative. But this implies just a manipulation, and this will give you the result 0 less than e to the power 1 by x which is less than minus x for all x negative. So, when x tends to 0, when x tends to when x tends to 0, then what happens this, the from the left hand side this will be 0. So, this limit comes out to be 0 because so this implies limit of this e to the power 1 by x when x tends to 0 from negative side is 0. Therefore, this limit is done. So, we have seen the 3 example. One is when the left hand limit and right hand limit both exist, but they are different. Second case, when none of the limit, the left hand limit nor right hand limit exists, it comes out to be infinity or minus infinity. While in the third case, we have only the left hand limit exists, right hand limit does not exist. So, the concept of the left hand right hand limit basically depends on the existence of the left or right hand limit depends on the function. Okay. And when both these limit coincide, then we say the function has a limit at the point x is 0. So, that is okay. Now, the equivalent definition in terms of the sequences. So, this is the equivalent definition of left and right limit, left oblique right hand limit of the function f x at C. This is in the form of theorem. Let A is a subset of R, let A be a subset of R, and let F is a mapping from A to R, and let C is an element of R be a cluster point, of A intersection C infinity. Then the following statements are equivalent. Equivalent. The first statement says limit of the function f when x tends to c plus, that the right hand limit of f is suppose L, then it is equivalent to the second statement that for every sequence action that converges to C such that x n is in A and always x n is greater than C. Strict means always toward the right hand side of the C for all n. For all n belongs to capital N, then